Hello, I'm Ty, and today I'll be breaking down the first problem from the Linear Algebra Final of 2025. So this problem is a classic linear mapping problem. It defines T, and the input is the variables a through e, and the output is here. The first question we're asked is to find the domain. So what is the domain itself? The domain is the set of all possible input vectors. And the way to best approach this, or the way that I approach this, is to look at the number of components in the input. And so since there are 5 variables, our domain is going to be R5. So similarly, the codomain talks about the set of all possible output vectors, and we will look at the components for the output as well. So even though there are 5 variables in the output, there are only 3 components because we only have 3 rows here. So since there are 3 components to the output, it's going to be an R3 codomain. So that means our linear transformation can be described as mapping from R5 to R3. So to find the matrix A that represents the linear map T, we look at the coefficients. We don't just take coefficients 2, -1, and +3. Instead, we need to go variable by variable. So we'll start with A's. We have 2 A's in the first row. B's, there are none. C's, -1. D's, again none. And then E's, there are 3. Here we have none, then 3, then none, then 4, then, -4, and then none again, and then just the coefficients from everything on the bottom. That is our matrix A that represents the linear map. Now, D asks us to augment that matrix with X, Y, and Z, and row reduce the augmented matrix to find the range of T in terms of X, Y, and Z. And we're not allowed to use the pivot column shortcut. All right. So the best thing about this problem here is it tells you exactly what to do. Sometimes it's pretty hard to remember how to find the range, and this problem gives you the steps to do it. So clearly, the first step is to augment the matrix with X, Y, and Z. I'll save our time and copy this from here. So we'll augment this with X, Y, and Z. And now we will row reduce, as the question asks us to. Okay, looking at this here, we have a really nice relationship. It looks like this can just go right into that, and then we'll get ourselves a nice set of zeros there. So, of course, this is unchanged, so we'll just copy that down. This one is unchanged as well. We'll copy that one down. 2 of the top row plus the bottom row, that's going to be 0. That's going to be -3. Also 0, and also 0. Nice. What have we done? We've taken the third row and added 2 of the first row. And this is a very satisfying relationship. It looks like the third row is just an inverse of the bottom row, of the middle row, pardon me. And we will use that middle row to get rid of the bottom row. So these are unchanged, and the bottom row becomes all zeros. And what do? We took this, and we just added the middle row to it. So how do we find the range from this? It comes from understanding that the information comes from the last row here. So this relationship tells us that 0 is equal to Z plus 2X plus Y. Now this is an acceptable answer for your range. I personally like to isolate Z, but since this answer here, it will work. So what is this relationship here? It is a plane relationship. And that's exactly what we'd expect from what's going on. It's a plane relationship in 2 dimensions. And that's what we'd expect when we have 3 rows, but one of them is dependent. So our range is described by this plane, which goes through the origin, and that's an acceptable answer for the range. Now we'll express this range with basis vectors. Okay, so every vector in the range can be expressed as X, Y, and Z, and we just found out that we found out that Z is equal to -2x minus y from the previous step. Here, I'll put the transformation there so you can see it. And then we want to change this by factoring out the x's and the y's. So we'll start with the x's. We have 1 in the top, none in the middle, and -2 on the bottom. Take the x out. And added 0, 1, -1 on the outside. So you can do this could be your answer if you wanted to define these, but I think a more elegant way to look at this is to consider the range as the span of vector 1 and vector 2, where vector 1 is 1, 0, -2, and vector 2 is 0, 1, and -1. And again, this confirms what we saw previously, that the range is has 2 dimensions, because we've got 2 variables here. So explain your answers for part D and part E and mention these 4 vocabulary terms. Okay, so I'll type this. So part D describes which vectors are in the range with the constraint that we talked about, which was y equals -2x minus y. Pardon me, this is z. Which defines a vector space, right? Because that itself is the plane that we talked about that goes through the origin. Part E shows the same vector space as the span of 2 vectors, v1 and v2. Every vector in the range is a linear combination of v1 and v2, and both parts describe the same 2-dimensional plane, but part D does it with an equation, whereas part E does it with span. Find the kernel / null space. Okay, so what's the kernel? The kernel is what maps to, it's the vector space or the set of vectors that the linear transformation T maps to 0. So the way we do this is you can think about it how we did the previous problem where we augmented it with x, y, and z. We can augment our matrix A with zeros. So let's copy down our, I have this copied. So here is our matrix A. And instead of putting x, y, and z like we did for range, we will just put zeros here. We'll do the same as we did before. 0, 0, 0, of course. And then, okay. We can just, we'll go through it. So then this is a 0, this is a -3, this is another 0, 4, and a 0 as well. And then hope you can see, as we saw before, that bottom row becomes all zeros. So what's different about this problem compared to the range problem is that instead of looking at this relationship here, we look at the relationships up here in terms of the coefficients. So these numbers here aren't just random numbers, they actually represent coefficients as well. So we can look at some of the key relationships here. Looking at the first line, we can think of this as A, B, C, D, these representing the columns that they're below. So looking at the first row tells us that 2A minus C plus 3E is equal to 0. And the second row tells us that 3B minus 4D is equal to 0. We can isolate for A here. So we get 2A is equal to C minus 3E, and A is equal to this all over 2. And then isolating for B, then we get b is equal to 4 over 3d. So in a similar way, we can remember that the original space can be described as this. And then with our new understanding of some of the definitions of these, we can plug in their equivalents, and b, remember, is equal to 4d over 3, and then c, d, and e are independent, so they remain unchanged. So now we want to factor out and reduce to eventually find the basis definition of it. So we can do the span definition again, which is much more elegant. We'll start with c. So how many c's in the first one? There's 1/2, because if we assume everything else is 0, then this whole thing will disappear and we just have 1/2. So we have 1/2 there. And then we have nothing, 1, 0, 0, 0, right? This is times c. And then we'll do the d's next, 0, 4 over 3, 0, 1, 0. And then the e, which is -3 over 2, nothing, 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 1. Okay, and then we can describe kernel of t is equal to the span of v1, v2, and v3, where, and we're going to continue down here, where v1 is equal to 1/2, 0, 1, 0, 0. v2 is equal to 0, 4, 3, 0, 1, 0. And v3 is equal to -3 over 2, 0, 0, 0, and 1. This is a nice span definition of kernel. Let me just double check those answers. Okay, that's right. Without using the rank nullity theorem, find the rank. All right, what the heck is the rank? So the rank is the dimensions of the range. Now, we'll go back to when we saw the range over here. We have two variables here, so that means our rank is 2 dimensions, and we did see already through two different proofs that our range was a plane that went through the origin. So that means it has 2 dimensions, and that means our rank is 2. Okay, and our nullity is going to be equal to the dimensions of the kernel. And going back to solving for the kernel, we see that our definition is formed by 3 basis vectors, or it has 3 variables in its factor definition. So this one is going to be equal to 3. Okay, does T justify the rank nullity theorem? Justify your answer by referencing your work and include justifications for your calculations of rank and nullity. All right, what is the rank nullity theorem? That asserts that the dimensions of the original domain of T is equal to rank plus nullity. And the dimensions of the original domain, if we recall, so the original problem, the domain was R5. Our rank and our nullity is 2 and 3. And the dimensions of R5 is 5, and that checks out. So it fulfills the rank and nullity theorem. And to truly reference your work, you could point back to this is A, and then this is H, and then this is I, part I. Okay. Is it injective, surjective, or bijective? And justify by referencing your work. So what does it mean for something to be injective? So from the way to approach it from this problem, our definition of injective is going to be whether the dimensions of the kernel of t is equal to 0. And then we'll come back and prove these later. We'll see, so the definition of surjective will be if the dimensions of the codomain is equal to the rank. And then the definition for bijective is both injective and surjective. Okay, so let's go over some of these definitions, or let's try to figure out whether these fit what we're working with. So we want, if it's injective, we want the dimension of the kernel to be 0. And we already see here that the dimension of the kernel is not 0, but it's 3. So clearly that's wrong. So not injective. Okay, and then you could quote this if you wanted to justify your answer by referencing your work. You could say this is from part H. Okay, and then surjective, dimensions of codomain is equal to the rank. And let's recall that our codomain is R3 and our rank is, right, the rank is 2. So that comes from part H. This one comes from part I. And clearly 3 is not equal to 2. So this one is not surjective either. Okay? And for something to be bijective, it must be both injective and surjective. And since it is neither, it is not bijective. So I hope this helps. This is a very classic problem. When it comes to linear mapping, you should know how to do all this stuff. And last note, I want to apologize for my voice. It sounds horrible. I have the flu. So I hope that didn't mess up any problems with clarity. Okay, I'll be making 4 more videos addressing the other 4 problems from the linear algebra final. And I hope this helps.